Hello, good afternoon. My name is Deanna Southard, and today I will be presenting about the GRASP design principles for CSI 5448. And here's a table of contents. We're going to cover an introduction, why these principles are used, what they are, and quickly talk about these principles versus the Gang of Four patterns we've discussed in class, and then I'll have my conclusion. So, as an introduction, GRASP stands for the General Responsibility Assignment Software Principles or Patterns, depending on where you look it up. And they are essentially a learning aid to help understand object design by applying design reasoning in a methodological, rational, and explainable way. And these principles offer guidelines on how to assign responsibilities to all the different classes and objects in your software, following an object-oriented design. So our inspirational quote is that the critical design tool for software development is a mind well educated in design principles. It is not the UML or any other technology. And this is the design or the inspiration behind having principles instead of just following some sort of tool. So why use GRASP? So these GRASP principles are not a one-fit solution to any specific design problem or software problem that you encounter. Instead, it's a philosophy of design. And if you want to use them properly, you need to understand what problem you're facing in your specific design. You need to thoroughly understand exactly what problem you're facing, and then use the GRASP guidelines as detailed in the different principles to come up with a robust solution for this design problem. And if you follow these principles, it'll lead to an improved design and improved architecture in your software. The name GRASP was chosen because you need to grasp these principles to have successful software design in an object-oriented fashion. So there are 9 core principles. They are the creator, information expert, controller, low coupling, high cohesion, polymorphism, pure fabrication, indirection, and protected variations. And many of these sound familiar to what we've covered in class already. I'll be going through them one by one, and to demonstrate all of these different principles, I'll be using a Monopoly board game example, and I'll be performing this demonstration in time with this presentation. So I'll present each principle, discuss it, and then I'll show a demonstration of that principle illustrated by this Monopoly board game. And this domain model is the one that we're going to be playing. So there's a Monopoly game, and it's the player plays a Monopoly game. The Monopoly game is played with some die, and also is played on a board. The board contains many squares, 40 of them exactly, and then there are pieces that the player owns that are on squares. Most people have played Monopoly and understand how it goes, and so this will be an easy example to follow along with, and hopefully this example will help illustrate all of these different principles. So the first one we're going to be talking about is the creator principle. So the problem is, who creates an instance of a new class? And the solution, according to GRASP, is to assign the class the responsibility to create an instance of another class if class A aggregates class B, or class A contains class B, if class A records instances of class B, if class A is closely uses class B, or if A has the initializing data that is needed while creating class B, and we would call this instance A would be an expert with respect to B. So for the approach to determine who should be a creator, you need to look closely at the domain model, and you should ask, who should be creating what classes. And the way you would figure that out is look for the classes who contain other classes, and those classes should be assigned the responsibility of creation. And as an example, in Monopoly, you could look at all of the board square tile, all the tiles that the player pieces land on, and ask, who should create those board objects. And looking at this domain model, you can see that the squares are contained within the board object. So the board object is the one who should be the creator. And so board would be able to create square objects. And so a benefit of that is it supports low coupling, and the class who's assigned the responsibility of creating other classes will it's not the class that's going to be necessarily using them. It'll separate the logic between creation and actual execution. One of the problems with this would be that sometimes your creation might have significant complexity, and in those times there's tight coupling between the creator and the created class. And you also, in some languages, you need to take into account the task of destroying objects, like C++. Java, you don't have to worry about garbage collection, but in other languages, you do need to worry about garbage collection. And usually, you can put together garbage or creating and destroying classes for performance reasons. Okay, the next principle we'll be discussing is the information expert. So in the real world, any application could have hundreds of classes, and you'll have thousands of actions with all of those classes combined. So how do you start assigning responsibility? And so the solution would be to assign responsibility to the information expert of that particular action or class, and the information expert is the class that has the information necessary to fulfill that responsibility. So what you're going to do is state that responsibility very clearly, look for any class that has the information needed to fulfill that responsibility, and assign the responsibility to that class. So for instance, in Monopoly, when you land on different squares, different objects need to be able to reference whatever particular square you're on. So for instance, your piece, when you move it, when you roll a dice and you have to move, you need to figure out what square you're going to be moving to, and then what actions occur once you land on that square. Now since the board contains all of the squares, the board is the one that's going to have all of the information necessary to fulfill the responsibility of telling the player pieces which square it's going to be landing on, as well as the actions that are going to be incurred once upon landing on that square. So the benefit of this is that you maintain your encapsulation, as objects will use their own data to fulfill the task, and it will also support low coupling. Additionally, responsibility is distributed across all the classes that have the required information, and this encourages highly cohesive and lightweight classes. However, one problem with this is as you start assigning these responsibilities, you might come up with lower level responsibilities, and this can lead to more work. It could also lead to realizing that assigning one class a certain responsibility, it may not be suited for the lower level responsibilities, and you may have to start over. But when it works, it's really good. So 3 is the controller principle, and that problem that this addresses is who should be responsible for handling a system event. And the solution is you want to assign the responsibility for handling system events with one of the following messages or ways. You'll either want to create a class that represents the overall system, and this is a facade controller. You'll either, otherwise you can create a class that represents a use case within that particular system event, and this is a session controller. You could have something that represents the overall business, or something that represents something in the real world that is active, and those are facade controllers and role controllers respectively. So what you will do is look closely at the domain model to find out where you have a family of classes doing any sort of work or job pertaining to a specific function, and that would need a facilitator for that function. and you will add a new class to take the responsibility of that controller, where all the client code is going to access the functionality through this new class that you created. And for example, looking at the left-hand side of this picture, the first thing that happens when the human player opens a Monopoly game, assuming this is an electrical or a computer game, is that you turn on the button to play, or you open up the game to play, and the first message that is getting sent from, in this case, if this is a Java game, from the JFrame is a play game message. And initially, while you're trying to figure out what you should be doing, who should be picking up this message, you would consider having a class that would represent the overall system, in this case, of your game. And that's what you see here, is that this Monopoly game class is going to represent the entire system of the Monopoly game, and it will be intaking this play game event coming from the human actor, and behaving and addressing that input accordingly. So a benefit to this principle is that we again support low coupling, and also promotes understandability and maintainability, because once you understand, you'll be able to easily see where events are handled, and that class will be a standalone class. So if you need to change simply how events are handled, you can change that class. If you need to change how events are handled in a layer underneath that, then you can swap out lower levels, lower layers, much easier than not having that individual class that takes in the events. So one problem is that sometimes while you're designing the systems, is that you can start grouping the responsibilities of different events that are coming in. You might group them all together into a single class. Like you might have one. You might design one single class, so like take in all actor inputs, instead of having, and this might result in something called bloated controllers, where your controller is trying to handle too many system events. So if you were designing something that would take an input in from the computer, it's much better to have a controller that would take in inputs from, say, the keyboard, and then a separate one that would take inputs from the mouse, and a separate one that would take inputs in from the touch screen, instead of trying to group all of those three responsibilities together. And the bloated controllers can be avoided by adding more controllers and separating out that responsibility. So number 4 is low coupling. And how do you want to reduce the impact of changes and encourage reuse? This is a problem that this principle is addressing, and the solution is that you need to assign responsibility so that coupling remains low. And as we covered in class, coupling is the manner and degree of interdependence between software modules. So your approach will be to look closely for classes that have many associations to other classes, and look for methods that rely on a lot of other methods, and rework the design to assign responsibilities to different classes in such a way that they have lesser responsibility and there's lesser codependence. And for example, right now in our Monopoly game, the board object is the only one that gets the square object. But if instead we had it so that every time you rolled, your individual piece went and asked the square object for a new square tile, we would have more coupling between the pieces and the square, and that would result in higher coupling, which is a bad design practice. So benefits of having low coupling is that when you do need to change one class, there's little to no effect on the other classes that aren't being changed. So this improves the maintainability, and also improves the reusability, because if you have one class that works really well in one application and you move it to another application, as long as the inputs and the outputs are the same, you can mix and match your classes and have no bad effect to that, so long as coupling is low. And this also means that it's easy to understand. You could look at each module as its own piece, and you don't have to keep referencing other modules to understand the big picture. Unfortunately, one liability of this particular principle is that it's impossible to remove all coupling, and it would be unrealistic to try to attempt to do so. And in some cases, coupling isn't necessarily bad, such as using some very stable classes like list arrays. If you're highly coupled, or if you're like medium or directly coupled with those classes, it's not a bad thing in those specific cases. And attempting to remove all coupling in a software is unrealistic, and it'll require a lot more work than is really necessary or is beneficial. So number 5 is high cohesion. And how do you keep your classes focused and manageable? And the solution is to assign responsibilities such that cohesion remains high. And cohesion is the degree to which elements of a module belong together. Looking back here, in the high cohesive diagram to the left, most of the pieces in the circle are squares. So they belong together. In the low cohesive environment on the right, the shapes are much more varied. It's not so clear how they all are grouped together. So what you're going to do is look for classes that have too many disconnected methods, or methods which do a lot, and you could probably break them into different individual methods which do more focused work. And then you will assign responsibility to classes such that all of the responsibilities in the class, all the methods in that class, are related instead of being highly varied. So an example is, if the Monopoly game controller, game class is the controller, if we had the Monopoly game class doing all of the actions, like rolling the dice, or moving the player's pieces, or drawing a community chess card, they're all very different actions that this Monopoly game class is performing, and it ends up with a very low cohesive class. However, if we broke it up such that instead of doing all the work itself, the Monopoly game class called it different classes which in themselves performed the actual work, and that work was all very closely related, such that there was like a dice class that would roll the dice. There'd be a piece class that would keep track of the player's piece and move it accordingly. Then that would result in a very highly cohesive environment, and it's a better design. And the benefits of this is that it's very clear and easy to understand why the design is out the way it is and how to follow along with the different method calls. And then again, maintenance and enhancements are simplified because you're dealing with small chunks that are very closely related and that are very focused in their direction. This also supports low coupling, and it also results in smaller size classes with very high related functionality. And if you have a small tool that does its job well, it's easier to reuse that tool in different applications. So one problem is that there are some scenarios in which it's desirable to have less cohesive environments, such as the case of a server object. In that case, the performance matters more than anything else, and so instead of having many different smaller tools, it's better to have a single interface with many unrelated operations just because it improves your performance. So there are some occasions when cohesiveness is not the most important thing. So number 6 is polymorphism. And as you can see in the picture, say the one action could be construed in different ways depending on the class that's responding to the action or the method. So the problem is how to handle alternatives based on type and how to create a pluggable software component. And the solution is you will assign behavior using polymorphic operations for the for types of classes in which you expect the behavior to vary. So what you will do is you'll identify which classes you would expect behavior to change, slightly, or not too much, because if it's too much of a change, then maybe it should be a whole different class, not even abstracted, similar to the duck and the rubber duck example that we've covered in class. If they're too different, then they should not be related. But if they vary different, just slightly, then you can look for methods which use conditional statements before you change it into polymorphic abstracted classes. And this would be like if you looked at a method where it said, if duck do this, if cat do this, if dog do this. Instead of having all those different conditional statements, you can instead abstract a superclass and assign responsibility to a type of behavior for which that to a type for which that behavior varies. So you'll have a superclass that will be responsible for an abstract method for all those individual subclasses, and those subclasses will have the varying behavior. And a good example of this is in Monopoly. When you land on different squares, your player will have to undergo different actions, such as if you land on go, you collect $200. If you land on a property square, if it's not bought, you can buy it. If it is bought, you pay rent. If you land on the income tax square, then you have to pay your income tax, and so on. And so you could have an abstract square object with an abstract landed on method, and that method would be implemented in all the different individual square types with all their unique behaviors. And the benefits of this is that it's very easy to extend unknown variants. It's very easy to add more types of the same abstracted class. And this also means that maintenance and enhancements are again simplified, because if you need to change something in a single type, it doesn't affect all the different classes, and you don't need to search through a ton of code and other classes. You can only look in the single class that you need to affect. And if you need to change the behavior for an entire grouping, for instance, if you need to change all of the behavior for all the squares that all the players land on in a specific way, it's very easy to do that without having to change that behavior in every individual class. One liability is that code that would be initially simple might become unnecessarily complex as you try to abstract out classes and implement this polymorphic behavior. So it might not be good for very simple code that isn't expected to become complicated later. So number 7 is pure fabrication. And looking at this, you can see between sale and database A, the broker needs to have a rectangular shape. But between sale and database B, the broker must have a triangular shape on the database side. And the problem that this principle addresses is who should be responsible for when an expert violates high cohesion and low coupling. So looking at your information expert, you want to assign information experts to classes which have all of the knowledge necessary to fulfill a certain responsibility, and occasionally that might result in higher coupling than you would wish for, and also lower cohesion than you'd wish for. So what you would do for the solution is you would assign responsibility for handling a system event to a new fictitious class that doesn't represent any concept in the domain, but it's there sort of as a filler in order to maintain low cohesion and high coupling. And so what you would do is look at the domain model and look at places with low cohesion and high coupling, and create a new class to take the responsibility of the functionality that causes this low cohesion and high coupling. And remember, we want low coupling and high cohesion. So this artificial class will help alleviate that bad behavior. So, for instance, in our Monopoly game, we have dice, and you have dice that are used in many players. And so, if you have it, if you put it in the player class, the responsibility for rolling and summing the dice, then it's impossible to generalize that dice and to be able to use it in other classes. And it also makes it difficult, not as straightforward, to simply be able to ask what the total is instead of rolling again. You'll have to come up with a new method to ask for the total. Instead, you could have a filler class, an artificial class called a cup. And then that cup will be responsible for holding the dice and rolling them and having the number of their total ready for whenever the player asks for it. That way, if the player asks for it and asks for it again, that's the same method, and the player doesn't have to come up with a different method of roll and then roll without, or get the number without rolling again. It reduces that method. It reduces the complexity of the code altogether. So benefit is it supports low coupling and results in high cohesion, which is the entire reason of having this principle, and it also promotes reusability because now the cup class in our example can be used in other classes or other applications. And a liability is this does sometimes result in many classes which would have a single method, and it could seem like overkill if it's too drastic. So our next principle number 8 out of 9, is the indirection principle, and this is how to combine low coupling and high potential for reuse. And similar to our previous example, we will be assigning responsibility to an intermediate object so that other components are not directly coupled. And so what you'll do is look closely at the domain model and locate classes that have low coupling and use an existing class to take the responsibility of the functionality that causes the low coupling and also the functionality that has a high potential for reuse. And again, with our previous example, that cup object serves as an intermediate object between the player and the dice that reduces the coupling between player and dice, and it also contains the dice in such a way that it's much easier to remain reusable for other games and other applications. And this supports low coupling and results in very high reusability. And unfortunately, similar to the last principle, this again may result in a bunch of classes with a single method, which is kind of overkill. So number 9 is our protected variations. So the problem that this addresses is how should responsibilities be assigned in such a fashion that future variations in the system don't cause major problems. And the solution is to create stable interfaces around points where you suspect there will be or there currently are future variations. So you will look closely for objects with direct coupling or which are prone to being changed, and also identify other points where you predict there will be future variation and assign responsibilities around them in such a way to create a stable interface that is easily changeable and updatable in the future. So our Monopoly example are the piece objects. And I'm sure many of you have seen the different variations of Monopoly that are currently available. The original objects are things like the thimble and the dog, and you should design your piece object in such a way that it's easy to change them in the future because they are an object that seems to be easily and obviously going to be changed. And the benefits of this principle is that obviously new variations are easy to add to the classes that you planned on future variations occurring. And also, new implementations can be added without affecting clients. Coupling is lowered, and because it's easier to implement new changes and new variations, the overall impact and cost of those changes can be lowered. The problem is that your design costs of speculative future-proofing may outweigh the design costs incurred by a simple design that's reworked as necessary. So if you had a simple design that you didn't put in place easy future variation accessibilities, it might be easier and even cheaper to work in those future changes instead of trying to plan for every single possible future change and coding to protect against that possibility. And so, talking about the grasp versus our gang of four patterns, in class, all of our different patterns were tied to specific and recurring problems that developers regularly face when creating softwares, and we could almost use those patterns as a cheat sheet, so long as you figured out what problem it was that you were facing. You could look up a pattern that addressed that problem and simplified it and use that pattern for your specific problem. However, the grasp principles are not tied to any specific problem, and so it's not easy to find the exact solution to whatever you're facing. But the good side to that is that not being tied to any specific problem means that these principles hold true in any design scenario. And it's almost easy to understand these principles as some sort of abstract underlying principles underneath all of the gang of four patterns. Instead of being the single answer, it's the principles that the patterns follow when coming up with their own answers. So in conclusion, like all of those patterns, these principles, if followed correctly, will result in code and products and applications that are highly maintainable, robust, and very reusable, which is what we all really, really want. So I got all of my information from Mr. Craig Lerman's book, which is Applying UML and Patterns, and this book is available in our very own Chinook library. So if you ever need to find it, it's there in the engineering, math, and physics stacks. And thank you for paying attention to this recording. I hope you learned something.